Swayam Prabha. Digital India. Educated India.
Hello everyone. As you might recall, in our last class we started our discussion on the nature of electrons or the behavior of electrons in solids, and we started discussing 1D solids and moreover 1D perfect solids in which there is no defect, no lattice vibration. And in that sequence of discussion we saw that we cannot solve Schrodinger equation precisely for the potential profile in solids, but there is an approximation which helps us a lot in order to solve the Schrodinger equation analytically, and that approximation is known as the KP model that we will discuss in today's class. So, just to give a quick review, a 1D solid looks, a perfect 1D solid looks something like this. It has a long sequence of atomic cores. Atomic cores are positively charged, fixed and heavy particle, so to say, and in presence of these particles the potential profile, the potential energy profile of the electrons will look like this. So, this is like a long sequence, an infinite sequence of potential energy going to minus infinity and then going to an upper value and then again going to negative infinity. But this is not an exactly solvable potential profile in Schrodinger equation. So, that is why the Kronig-Penney model approximates this potential profile by a very similar looking profile, but we avoid the negative infinities in the potential profile, and instead we have the potential going from a lower value which is taken to be 0 here to an upper value which is taken to be u naught periodically to the extent of the entire solid. Okay. So, this is what we discussed in last class. This is what we will solve the Schrodinger equation for. But even for this potential profile, we cannot sort of solve the potential the Schrodinger equation for the entire extent of the solid, because it's like quasi infinite solid. It's a very long solid in which if we had to solve the Schrodinger equation for the entire solid, we would need to solve the Schrodinger equation for all the atomic cores corresponding to each atomic core. But here, as we saw in the last class, a mathematical theorem called Bloch's theorem helps us, and what Bloch's theorem says is that if the potential is periodic, which means ux plus a is equal to ux, where ux is basically the potential profile, then the wave function of the particle is given as psi x plus a is equal to psi x times e to the power I k a, where a is the period of the potential profile, potential energy. Okay. And we also saw that an equivalent statement of this theorem is that this psi x plus a, which means the wave function of the particle in this potential profile, can be written as exponential I k x, or sorry, this psi x can be written as, an equivalent statement is psi x can be written as I k x times ux, where ux is a periodic function, which means ux plus a equals u times ux basically. So, we also saw that these two statements of Bloch's theorem are equivalent, But what is the physical implication of Bloch's theorem? Physically, it has made our job very simple, because now we need to solve the Schrodinger equation in just one period of the potential profile. And by using the Bloch's theorem, either this statement or this statement, we can find out the wave function of the electron or wave function of any particle anywhere in the solid. Okay. So, this is the power of the Bloch's theorem. This is highly useful theorem, especially in solids, or especially for potential profiles which repeat itself after certain distance. Okay. So, today we will see how the electronic wave function would look like in a 1D solid, and for that we would first need to define a single period of the potential profile, which means we would need to see how the potential energy looks like in a single period of itself, because the potential profile is periodic and it repeats itself after certain time. So, first we need to identify a single period or single length in which potential profile is not repeating itself, and then we would need to solve the Schrodinger equation for this period. Okay. After that, by invoking Bloch's theorem, by using Bloch's theorem, we would be able to find out the electronic wave function everywhere. The wave function can be find out any where in the solid. Okay. So, in this particular potential profile, if we closely look at this, we see that in this particular range of x values from here to here, from this point to this point, this boundary to this boundary, there is a single one iteration of the potential energy, and after this the potential profile repeats itself with the same frequency basically. Okay. So, just for the sake of convenience, we define this point to be and the x equal to 0 point, we define this point to be x equal to a, and this point to be x equal to minus b. So, in this case the potential is having a certain pattern from x equal to minus b to x equal to a. Okay. And there is a jump in potential at x equal to 0, which is visible in this figure. And then this particular pattern from x equal to minus b to x equal to a, it repeats itself throughout the entire solid. So, in this case the period of the potential profile would be just a plus b. So, the potential repeats itself after a plus b distance in space in this particular 1D solid. So, with this this background, we are now ready to sort of solve the Schrodinger equation. So, the potential in this single unit cell for potential profile looks like this, minus b to a, and then it repeats itself. And as we have seen, a repeating potential or a periodic potential, for a periodic potential we just need to solve the wave function for a single period, and later on we can extend this wave function to the entire solid by using the Bloch's theorem. So, in this case, in a single period of potential, as visible from this figure, there are two regimes of potential. From x equal to 0 to x equal to a, the potential energy of the electron is 0. From x equal to 0 to A, and the potential energy of the electron between minus B and 0 is u naught. So, ux is 0 for x greater than 0 less than a, between 0 and a, and ux is a constant u naught between minus b and 0. Okay. And since there is since the potential energy is different in these two regimes, we would need to solve Schrodinger equation differently in these two different regimes. Okay. So, that is what we will do now. We will solve the Schrodinger equation in these two regimes. Okay. So, let us say this is regime A, this is regime B, and as is clear, the period of the potential profile is A plus B. I would take a pause here and sort of bring it to your notice that here this k parameter, it comes from the Bloch's theorem. In our earlier derivations, this k parameter was coming from the derivation of the Schrodinger equation, but here it is coming differently. And if you go through the derivation of Bloch's theorem in any textbook, you will see this k is still like the wave number, it still corresponds to the momentum of the electrons in the solids, but it's slightly different from all previous cases. Physically, it is still the momentum parameter, and in this case it is known as the crystal momentum. We will see that later on. So, first we will solve the Schrodinger equation, and in regime A the potential energy is 0, and regime B the potential energy is u naught. Regime A and regime B. Okay. So, in regime A, the Schrodinger equation would look like minus del 2 by del x2. Let us say the wave function here is psi ax plus ux psi x equals E times psi a x. Okay. But in this case, in regime A, ux is 0, so it essentially is, and there is minus h square by 2m as well here before del 2 by del x2. So, it would look like del 2 psi a x by del x2 plus 2m e divided by h bar square psi a x equals 0. So, this is quite like the Schrodinger equation for a free particle. So, this is the Schrodinger equation in regime A of the potential profile. In regime B, the potential energy is u naught. So, the Schrodinger equation now would look like minus h square divided by 2m psi b x plus u naught psi b x. The wave function in this regime is basically psi b x, represented as psi b x, equals energy of the electrons psi b x. After rearranging these terms, we can see that this can be written as, and there is a double derivative here, this can be written as del 2 psi b by del x2 plus 2m times E minus u naught divided by h bar square psi b equals 0. So, this is the Schrodinger equation in regime B. So, let us sort of put them together at one place, and as you might have already noticed, the Schrodinger equation looks quite like the our earlier Schrodinger equations that we solved for free particle and particle in a box cases. So, putting them together, Schrodinger equation for regime B would be del 2 psi bx by del x2 plus 2m e minus u naught divided by h bar square psi bx equals 0. Okay. So, this is regime A and this is regime B. Okay. So, so this parameter can be defined as sort of alpha parameter, alpha square. Let us define it to be alpha square, and let us define this to be beta square, as is clear here. So, once we sort of encapsulate this energy term in alpha and beta, then we can easily write down the solution of these Schrodinger equations in terms of sines and cosines, as we did earlier in case of free particle and particle in a box. So, the solutions of the Schrodinger equation will look like this. In regime A, psi Ax would be given as A sin alpha x plus B cos alpha x, and in regime B, psi Bx can be written as C sin beta x plus D cos beta x. So, these two are the solutions of the Schrodinger equation in regime A and regime B respectively. As you can see, there are 4 unknowns here, and in order to precisely find out the values of these unknowns, we need to use boundary conditions, as we did in case of particle in a box case. Okay. So, please remember these solutions, especially the free particle solution and particle in a box case, because these two solutions are easy to remember first of all, and second, these two are heavily used prototypes solutions in almost all quantum mechanics, especially in solid state physics. Okay. So, please keep those things in mind, and now we need the boundary conditions for this particular system, and so there is one boundary here at x equal to 0. Okay. So, the boundary condition at x equal to 0 basically means that from the postulates of quantum mechanics, we can easily, you might have easily guessed that the first boundary condition would be that the wave function should be continuous at x equal to 0. What it means is that psi a, which is basically the wave function in regime A, at x equal to 0 should be equal to psi b, which is the wave function in regime B, should be equal to psi b x at x equal to 0. So, the first boundary condition would be that psi a 0 should be equal to psi b 0. That comes from the continuity of the wave function, as we discussed in the postulates of the quantum mechanics. Okay. So, this is the first boundary condition that we would use. The second boundary condition is that the derivative of the wave function should be continuous. which means that derivative of psi a at x equal to 0 should be equal to derivative of psi b at x equal to 0. So, these two boundary conditions we obtain from the basic postulates of quantum mechanics. Okay. But there are 4 variables and we need at least 4 conditions to solve for all 4 unknowns here, these a, b, c and d. So, the other 2 boundary conditions will come from the Bloch's theorem itself, and according to this theorem the potential, as you can see in this single unit of potential profile, the potential profile repeats itself after the interval of a plus b. So, it means that the potential here and here are again same. Potential at x equal to minus b is again same as potential at x equal to a. So, what it means is that psi at x equal to a is psi at x equal to minus b times a plus b. So, this comes from the Bloch's theorem, from this statement of the Bloch's theorem, and similarly a similar statement of Bloch's theorem holds true for the derivative of the wave function, and from there we can see that del psi by del x at x equal to a should be equal to exponential I k a plus b psi x equals to minus b. Okay. So, this psi x equal to minus b is basically psi b function and psi x equal to a is psi a function, similarly here and here. So, now these are the 4 boundary conditions that we will use in order to find out these 4 unknowns a, b, c and d in the solution of the wave function. Okay. So, once we can find out these 4 sort of, once we solve these 4 equations, if we solve, so for example, if we solve the first equation, first boundary condition, now things are getting, the maths is getting slightly involved as we are progressing in real systems, and that is the characteristics of quantum mechanics. For most of the practical systems it is mathematically difficult. So, in this if we use this boundary condition psi a at x equal to 0, so if we put x equal to 0 in this case, the first term would be 0 and the second term would be b times 1. So, this boundary condition says that psi a0 is b basically and psi b0 is similarly d. So, this says that b should be equal to d. And the second boundary condition says that if we take the derivative of the wave function psi ax, it would be a alpha cos alpha x plus b alpha minus sin alpha x, and at x equal to 0 it would be a times alpha and similarly it would be c times beta. So, these are 2 conditions or 2 relations that we obtain from the boundary conditions. So, from the boundary condition, from these 2 boundary conditions we can directly see that b should be equal to d and a alpha is equal to c beta. C beta. This is regime A, this is regime B. The wave function in regime A is a sin alpha x plus b cos alpha x, and wave function in regime B is c sin beta x plus d cos beta x. Okay. So, we have already obtained two constraints which will give us the values of these constants, and the other two constraints can be obtained from the boundary conditions arising from the Bloch's theorem. And if we use psi a equals a, psi a at x equal to a, it will be a sin alpha a plus b cos alpha a, that should be equal to exponential. So, this a sin alpha a plus b cos alpha a should be equal to exponential I k a plus b psi b at x equal to minus b, which is psi b at x equal to minus b would be c sin minus beta b plus d cos beta b. So, this is the third, this is constraint number 1, this is constraint number 2, this is constraint number 3, and the fourth constraint will come from the derivative of these wave functions, which is essentially, so if we take the derivative of psi a with respect to x, it will be a alpha cos alpha x minus b alpha sin alpha x, and its value at a would be a alpha cos alpha a minus b alpha sin alpha a should be equal to exponential I k a plus b derivative of psi b at minus b x equal to minus b. So, derivative of psi b would be c beta cos beta x minus d beta sin beta x, and at x equal to minus b it would be c beta cos beta b plus d beta sin beta b. So, this is constraint number 4. So, we have 4 constraints, 4 unknowns are there a, b, c and d. In principle, by using certain mathematical techniques, we can solve these constraints and we can find out the values of a, b, c and d. So, we can easily replace b by d in constraint number 3 and 4, and we can replace a by c times beta by alpha, and by putting these values of b and a in equation 3 and 4, we will be left with only 2 constraints, and these 2 constraints can be solved or will have a non-trivial solution if the determinant from or determinant of the coefficients of the unknowns in these constraints is 0. So, this is a standard mathematical technique from matrix algebra, that these 2 constraints will have non-trivial solution when the determinant made from the coefficients of the unknowns will be of value 0. Sorry. So, finally, by putting the determinant of the coefficient to be equal to 0, this is what we finally obtain. This is the final relationship that gives the valid solutions of the Schrodinger equation. On the left hand side, we have this parameter, which is essentially E by u naught. On the right hand side, the left hand side is a function of E, as you can see, and the right hand side is a function of k. Just apart from these 2 things, all other parameters are system parameters or constants. So, there so in a way, this equation is basically tells us about the relationship between the energy of electrons that can exist in a solid and the k values that these electrons can take in the solids, or in other words this is the EK relationship for solids. This constraint gives us the EK relationship between solids. Okay. Please remember, I would again remind you that this K comes from the solution of the Bloch's theorem, from the statement of the Bloch's theorem, and this is known as the crystal momentum or the momentum of electrons in a certain environment, and it is different from the K that we generally use in the solution, but physically mathematically it is coming from a different source, but even in Bloch's theorem it is coming from the solution of the Schrodinger equation. So, do not worry about that. Physically it corresponds to a parameter called crystal momentum. Okay. And again a mathematical solution is not impossible, it can be done, but a graphical solution would be easier to understand, which is our aim in this particular course. Okay. So, we will see how the solution of this equation looks like, and that will give us the valid results in this particular solid. So, if we plot the left hand side and the right hand side of this equation on this axis, on the same axis, we will get the solution, and that is what we will see in the next class. Okay. So, thank you for your attention. See you in the next class.